Okay, good afternoon, everyone. Welcome to today's QuMat seminar. It's my pleasure to introduce today's speaker, Professor Katharina Franke from the Freie University in Berlin. Katharina did her studies in Kiel and then moved to the Freie University in Berlin to do a PhD with Karl-Heinz Rieder on quasi-crystals, if I'm not mistaken. She got her PhD in 2003, then did a postdoctoral research project at the EPFL, and then moved back to Berlin, where she has been ever since. And in 2012, you got your own professorship there, where you have been ever since. Katharina is well known for her work on, let's say, the interplay between magnetism and superconductors. Two topics that are also highly relevant for our quantum materials consortium, essentially, which is also one of the reasons why we invited her. And on a slightly personal note, I know that Katharina gives very, very nice lectures, which I'm hoping that you can also enjoy today. So, Katharina, thank you very much for accepting the invitation, and I'm sure that I speak for many that we look forward to it.
Well, thank you very much for the invitation, kind introduction, and the pressure build-up. So now I have proof that this is good. So yeah, thanks a lot. So I would like to talk about magnetic atoms on superconductors. Also, as Ingmar already mentioned, this is one of our main topics recently. And well, you see that we do this with a scanning tunneling microscope. And the idea is that we want to learn as much as we can about single magnetic atoms. And you will see actually different parts of how they induce subgap states in superconducting gap, how you can kind of engineer some of the properties and going even up to Josephson junctions and what the role of the magnetic atoms is there. Before starting, I would really like to thank the people who did the work. And this is first and foremost, basically, Eva Liebhaber in her PhD thesis did all the single atoms on niobium disolide that I will show, and Martina Trans did the Josephson junctions that will be in the second part. Well, I would also like to thank Felix von Oppen and his group for a lot of theory support. As you will see, it helps a lot, of course, in the understanding. So his PhD students, Harald Schmid, Larissa Menschek, and Jakob Steiner, and Kai Rosnagel provides nice niobium disolide crystals. Okay, so, well, it's about these Yu-Shiba-Rusinov states, but let me go one step back. So superconductivity is familiar to all of you. Of course, you can go, if you cool down the material that eventually becomes superconducting, essentially the resistance drops to zero below this critical temperature. Well, you all know that probably. Second hallmark of a superconductor is that it's a perfect diamagnet, so which means that you will expel all the magnetic field lines out of the superconductor, and that's the reason why a magnet would float on top of a superconductor. So, well, here you could say magnetism and superconductivity, they kind of seem to mutually be expelling each other and don't want to go together, but still there may be also some opportunities if you make these magnets very small. Now, you see here that you have a critical field and a critical temperature below which your material is not is superconducting, and above it's not. And another magnitude is also the current density. So if you have, let's say, a superconducting material and you want to push a current through it, you can also destroy the superconducting properties if you go to sufficiently high current density. So with these three parameters, you end up with a kind of a phase diagram, and only below these critical magnitudes you are in the superconducting state. And so essentially what will be the questions of my talk is that maybe can you first of all look into what single magnetic atoms do? So kind of you could say that's the smallest magnet that you can have on a superconductor, or can you somehow else kind of, distinguish and control in which regime you are, whether you are in the superconducting state, meaning in the sense of that you have a supercurrent, or that you have a resistive regime, meaning that you are in the kind of normal state. Okay, but let me start with this part of, what is now the influence of this small single magnetic atom? And let me just say, first of all, we should consider whether this is a classical magnitude, a classical magnet, or whether this becomes a quantum spin. So, of course, classically, you know all about magnetism. This is a macroscopic magnet, but often also, even if you take a single atom, you say you have unpaired spin, so you kind of also have potentially a magnetic moment. And if you were to treat this classically, even the spin itself is, of course, a quantum property, you could say that it has a certain direction. But well, this is not the case. I mean, there's many interactions, and the spin degree of freedom and exchange scattering with the substrate leads to the fact that usually we should deal with all of these single magnetic atoms that we do in terms of quantum spins. And you will see that this becomes important in the remainder of the talk. Now, as I said, it's about exchange scattering, for instance, with the substrate that these quantum spin properties become important. And the first, you could say, okay, how do you detect it? And I will say that we will do this with the scanning tunnel microscope, as I said before. I also mentioned that we will do superconductors. And if you look back in the literature, the first magnetic signatures of single atoms on surfaces have actually been seen on top of a superconductor. So this is this seminal work of Ali Yazdani at the time in the Eigler group. And now, for instance, they take a magnetic atom, it was manganese, and they put it on top of a niobium surface. And then they measure it at roughly 4 Kelvin. Okay, so first of all, I mean, these types of graphs, they will be there for also the rest of the talk. So this is a differential conductance recorded as a function of the bias voltage. And for the superconductor itself, so if you measure on the plane substrate, you have this superconducting energy gap that's symmetric around the Fermi level. But what they have found at that time is that if you not measure far away from the atom, but just directly on top of the atom and you record the differential conductance, it looks slightly asymmetric. You will see that nowadays the energy resolution has increased, and there are also tricks to increase the energy resolution. But already with this slight asymmetry, and you see that something is going on in the gap, they said, well, this is actually the fingerprint of exchange interactions of a magnetic atom with a superconductor. So in a way, that was the first time that this exchange interaction was seen, but roughly at the same time, also magnetic atoms on top of metals have been investigated. And here, almost at the same time, these two papers came out saying that there would be a so-called condo resonance of a magnetic atom that is interacting, so exchange coupling to the electron bath of a metallic substrate. And here it is essential that you see the quantum spin properties only because of the spin degrees of freedom. So all your substrate electrons, they scatter at the impurity. And what it gives rise to is a feature at the Fermi level. And this feature in shape could vary due to interference effects. But this is the hallmark that there's a resonance with a certain width, and the width scales with the exchange coupling. And this is attributed then to this quantum resonance with a certain condo temperature. So in a way, also this exchange coupling is very similar. So many times people ask, okay, so I mean, here you have exchange coupling, here you also have exchange coupling with the substrate. So in a way, these phenomena are very similar. And you could also see, if you were to go to larger energy scales, you could also see potentially this condo outside of the superconducting energy gap. And you can scale these Yu-Shiba-Rusinov states with the width of the condo resonance to see that, yes, it is the exchange coupling, which also gives rise to both phenomena on the superconductor at the very same time. Just to be complete about magnetism on surfaces, let's see that if you were to reduce the exchange coupling with the substrate, for instance, by taking a thin insulating layer that you put in between, then you can see inelastic spin excitations. Again, you can measure by that the quantum spin properties. For instance, what you see here now, the differential conductance. Let's say if you measure just on an atom in this very first paper, you see nothing in zero magnetic field. But if you switch the magnetic field to sufficiently high values, you see inelastic steps symmetric in energy around the Fermi level. And this is because, I mean, before in zero magnetic field, basically, let's say there's no spin up and spin down in a way defined. It's flipping all the time. But if you split it, essentially, you split the energy levels. due to the Zeeman effect, and one is your ground state, one is the excited state. And this energy difference you can overcome with inelastically tunneling electrons, and by that you have this opening of a new tunneling channel. And obviously it doesn't matter in which direction the electron goes, therefore it should always be symmetric. So kind of this is the whole zoo of magnetic excitations that you can see on surfaces. But as I said, I would like to focus on the ones that are on top of a superconductor. So this ones. Now, I already mentioned that, well, there it looks like, okay, you see a tiny change in the gap, but what's the real, let me go back one step, but what should you see? And the idea is that, okay, I said that you have exchange scattering, and now let's just draw it in a sketch what you expect to see. So your substrate has a quasi-particle density of states, which is depleted around, symmetrically around the Fermi level, because you have the pairing of spin up and spin down electrons. So then there's no electron-like density of states here, which you could, let's say, tunnel in, because we probe, of course, this excitation spectrum in a usual tunneling experiment. But once you go beyond this energy, then you have sufficient energy to actually enter with an electron or also enter with a hole. And that's where you see this so-called BCS coherence peak, so from Badin, Cooper, Schriefer, if we are just in a normal S-wave BCS super. Okay, so this is what a plain superconductor should look like if you were to measure it. Now, if we have this magnetic adatom, and I said we have exchange scattering, then you could, in a simple picture, say, okay, you have your Cooper pairs, but now you have also a spin located on your magnetic atom. So now imagine that you have some exchange coupling, and let's say it should be antiferromagnetic. Then in a way, you could say you locally perturb this Cooper pairing, right? Because you have now a competing energy scale with that, with the pairing. It competes with the pairing. And therefore, you could say, well, that locally gives you some additional states, so you can more easily, for instance, tunnel now into the substrate because you have weakened this locally. And therefore, a state should show up inside of the superconducting energy. So this is at a certain energy, and the energy you can look at where is this energy? Well, it's inside the superconducting energy gap. This is delta, and here you look at the scaling factor where it is. There's one important term that scales with the exchange coupling. So that's J, the spin of the adsorbate, and this is nu naught, is the normal density of states. But I think that the most important thing to note is that exchange coupling dictates where your states are inside the gap. Now you also see that this should be symmetric in energy at positive and negative bias voltage, and this is the fact that a superconductor is always particle-hole symmetric. So also your excitations should be particle-hole symmetric. So that's why you should always see a pair of these Yu-Shiba-Rusinov states. But so you also see is that, well, I sketched them here as they don't have to be completely symmetric in intensity anymore. And the reason being that there's a second term that you could also have, and this is potential scattering. So this potential scattering I call here with a K. And essentially, in a simple picture, I mean, it's like in Coulomb scattering also, it's maybe easier to put an electron than to put a hole. And therefore, your wave functions associated to this state, they have different weight at the positive and the negative part. Okay, so now I hope I established the fact that a single spin can give states inside the gap. And let me point out one fact here is that, I mean, I know that also here in this department, Ingmar and Christiane and Daniel, they are looking at states that you want to couple on the surface. And often, I mean, you're lucky with the CO molecules in copper, they are sufficiently decoupled to see these nice states. Then people go to semiconductors to decouple it also from the bulk. But a superconducting gap is also a gap from which can be used to decouple the states. So here, the states, they are really well separated from any bulk. So this is why they should also be very sharp. And therefore, you could maybe think of also that you want to play with these states. Obviously, the drawback is that you have very small energy scales that you need to deal with. But for instance, you could also say, let's say you want to put lattices, or let's say start with 2, similar to what is done here in the department. So basically, 2 atoms now, eventually these states could also hybridize. So you would see a splitting, or at least that's what you expect to see. Okay, it's not only two, well, one too many. So also, let's say you can eventually put up larger structures or chains, and then of course the states. I mean, you have hybridization, and at some point, first of all, your energy resolution will be insufficient to separate all the individual states, but eventually you would also get band formation. Well, this has also been kind of interesting for topological states. So now before I was drawing you these two bands, they were separated at positive and negative bias voltage, but there are also theoretical predictions if you design your bands such that they overlap at the Fermi level, then there could be the possibility that you have opening of a topological superconducting gap now. And then you would be in the regime of topological superconductivity, and eventually, and this has been discussed a lot, that then you should be able, if you were to construct, for instance, a magnetic chain on the superconductor, which obeys these particular energy level alignment, then you should also get Majorana states at the very chain ends. Okay, so well, this to the rough background. So now let's say, do we see this in experiment? And therefore, I would like you to guide you through some single atom things. So these would be magnetic atom, just a single magnetic atom on niobium diselenide. I will go to the hybridization of two, construct also other adatom structures up to these chains to see band formation. So basically the steps that I was showing. Well, and then on top of that, I also told you that this particle hole asymmetry in the intensity is there due to potential scattering. And I want to highlight one example where this is not only the exchange coupling is important to induce these states, but on top of that, this electron hole symmetry breaking is important, and that will give rise to what we call a Josephson diode. Okay, so now let's start with these single atoms and small structures. And the substrate that we use is niobium diselenide. It's a bulk material, so we use 2H niobium diselenide, which is a superconductor if you go below a critical temperature of 7 Kelvin, which is well reachable at our experimental temperatures. We work typically around 1 Kelvin. Now, what else is the reason of choosing this? So it's a layered van der Waals material. So on one hand, you can easily clean it in vacuum, get nice surfaces. But on the other hand, it kind of has a quasi two-dimensional nature. And what has been pointed out in this paper by Tristan Krem's group is that any kind of magnetic impurity, so they have found them in the bulk, and they have also seen these Yu-Shiba-Rusinov states that you find here inside the energy gap. But they found that they were super long ranged over several nanometers. And they explained it by the fact that now you only have a decay of these states with 1 over square root of r, while if you take a bulk superconductor, a real three-dimensional superconductor, then they would decay faster with 1 over r. So this is great, because then if I tell you that we wanted to couple and let hybridize these Yu-Shiba-Rusinov states, then you want to bring these sufficiently close into that the states feel each other. So if you have long-range states, then it's easier to put, let's say, magnetic atoms in this interaction regime. And this has been done by Peter Liljeroth's group. They looked at magnetic molecules, and you also see that there's a difference whether you look at a single molecule or a dimer. So you see that these states are already hybridizing, precisely due to the fact that, yes, even at this large distance, you see that they can. Okay, I mean, I know that also here you use niobium diselenide. Let me just point out that for those who are not so familiar with it, the gap structure looks a bit funny. So first of all, let me note that we use also a superconducting tip, which could be, for instance, just a niobium tip that we prepare on a different sample. And the idea is that by that we get a better energy resolution, because otherwise any sharp structure that you wanted to probe, but then you have a Fermi Dirac broadened Fermi level, then well you wash out your features. While if you take another superconductor and sharp against sharp, its density of states is really nice and sharp. So essentially we increase our energy resolution. Now, that also means that you have to see that, okay, you need to break electrons, the Cooper pairs also in the tip to be able to tunnel. Therefore, there will be a point where there's no density of states to be measured. And only beyond that will be the features that are interesting to us. Okay, so then if you do a differential conductance spectrum, you see something that's nicely symmetric, and well, but now you say, where are my BCS coherence peaks? It's not a single sharp peak, but instead you see that you have these kind of double peak structure with a lot of features around. And this has been discussed because you have this very complex Fermi surface, and basically you have kind of a multi-band or highly anisotropic superconductor, and then you can get these type of shapes. I don't want to go into these details, just that to remind you that whenever we want to look at subgap states, I mean, you may be misled that this is already one of these Yu-Shiba-Rusinov states, but it's not. The shoulder is there of the bare substrate. On top of niobium diselenide being superconducting at low temperature, there's also a charge density wave. So this you immediately see if you take an STM topography. So we see that we can image the atomic structure, so the selenium atoms, that's the small corrugation kind of, but then there's on top of it a pattern which is roughly repeating every 3 atomic lattice sites, but only roughly. And therefore it's an influencer density wave. So for instance, you see that if we look into this area, it looks like the maximum of the charge density wave would just be between 3 selenium atoms, while here the maximum is coinciding really with one of these selenium atoms. Therefore, the patterns look different, but that's just due to the fact that, I mean, your periodicity is not exactly in registry with the atomic lattice, and therefore you see these 2 structures. Well, this is kind of a bug and a feature for us at the same time, because, I mean, now imagine that you were to deposit adatoms on top of this lattice. So here I just drew the adatom structure from the niobium diselenide on top, and I mean, what we expect is if you let your atoms reside on this lattice, they would fall into hollow sides of the selenium lattice. Okay, that's fine. So first of all, you notice that there are lattice sites where you have a basically a niobium below, or you don't have a niobium below. These are 2 distinct adsorption sites. But for instance, here you can have a adsorption site which is just on top of the maximum of the charge density wave, while here it would be impossible. Instead, you're very close to it. Now the question is, does it matter? And yes, it matters. So here I just indicate where 2 atoms are looked at, but in order to not avoid the rough corrugation of the atom, it's just indicated. On atoms that would sit directly on top of the maximum of the charge density wave, we get the blue spectrum. And if it's just next to it, we get this beige spectrum. Okay, first of all, I mean, you see they look very different. But let me go through the details. So like in the light gray background, you see just the superconducting gap structure of the substrate. So there's nothing to expect. And then here, the shaded area is the gap of the tip. So again, you should not, besides thermal excitations, nothing to see. But then this energy range becomes interesting. And here you see that there are states. So we just label them alpha, beta, gamma, delta according to their energies. And in the blue spectrum, you see there's this one at lower energies, then comes a beta one, then comes more, and so on. And there's something also here within the coherence peaks. And the beige one looks very, very different. And the idea is that, well, the energy depends on the charge density wave. And if you recall the very first equation of the Yu-Shiba-Rusinov state, there was this exchange scattering term Js times nu naught. And this is the normal density of states. And of course, that's modulated by the charge density wave. So therefore, it's expected to see variations in these Yu-Shiba-Rusinov states. But as I said, this is kind of a bug in the sense that, okay, now all your spectra will look different depending on where the atoms sit. But if you want to make atoms interact with each other, I mean, like you want better to have the best hybridization, you want the states to be at exactly the same energy. So therefore, we said, okay, then we have to put these atoms into equivalent adsorption sites, not only with respect to the selenium lattice, but also with respect to the charge density wave. And that means that we are kind of bound, let's say, to a distance that's at least 3 lattice sites apart. So for instance, we could start in putting atoms on top of the maximum of the charge density wave. And this is then 1 nanometer apart. So we need to rely on the fact that our Yu-Shiba-Rusinov states are long-ranged. Just direct exchange coupling in 1 nanometer is just negligible. Okay, but then the substrate nicely allows we deposit our atoms randomly on top of the surface at low temperature, but then you can push them around with the STM tip and construct the lattices if you like, or these chains. Okay, so now do we see this hybridization? I mean, otherwise I would not have introduced it at the beginning, but let's see how would this actually be seen in the experiment. So before I was showing one spectrum that was taken on one of these atoms. So here you see the topography always in an inset, in an energy range where nothing happens in the spectra. So therefore I can nicely overlay it. But now essentially what we do is, I mean, the blue spectrum has been recorded just right on top of the atom. But if we take spectra that are across this line and plot them in a color scale, you already see that there's variation on the spectrum depending on the distance. So not necessarily that on the very center you see the largest intensity. For instance, here you wouldn't, but you see it slightly further away. These alpha and beta states that are labeled here get much more pronounced. You see here that there are other states also in the high energy part that you see in the color plot, maybe even more evidently. And you see that there's the oscillation, and this is due to the fact that we have this oscillation with the Fermi wave. Okay, but notably alpha and beta are discrete states, and I will focus on these lower energy states more because there we see they are sharper in energy, so we can look more precisely at what happens if we put a second atom next to it. So next to this would mean like 3 atomic sites apart. So here's the inset of the two atoms, the topography. Now again, we take a line cut along this and plot it in the color scale. And first of all, you see here, I had only 2 dashed lines. Here, I need to already put more. So there's more states going on. Or just measuring just on top of these 2 atoms, you also see in the individual spectra that there are more of these peaks. More of the peaks is already great. And actually, it's twice the number of peaks. So which would agree with hybridization. But let me look more closely into this energy range here. So just this is zoomed in. So this is roughly the energy scale of where we have the alpha and the beta state of a single atom. And now we see, yes, you have twice the number of states, and they are different in their spatial extent. Without going to the details, I would say like there's one very characteristic thing that these states that you split in energy, which you can see even more nicely if you put these dashed lines because they are differently distributed in state. So this is just going through the atoms. So this is the center between the 2 atoms, this line. And you would see that one of the alpha states has large intensity while the other one doesn't. Same holds true for the beta state. There's one which is a nodal plane and one where there's large intensity. And this is the characteristics, of course, if you take a very simple model of hybridization. You start with a single state of the atom, you put 2 of them together, you do the linear combination of these states, and of course you get the symmetric one where you should see maximum intensity between the 2 atoms, but you also get the antisymmetric linear combination where you should see a nodal plane.
Right.
Sure.
Maybe then a very naive question. So I would expect the symmetric combination to be at lower energies.
Yeah, not necessarily. So in the sense of yes, that's what you exactly expect if you do, let's say, the hydrogen molecule. Yeah. But here it can be slightly different because you have this oscillatory nature of the YSR state. So the lowest one is not the symmetric linear combination is not necessarily the lowest energy one. That's due to this oscillatory, where you are in space. So that could, in principle, invert, not always. Yeah.
Thanks.
Yeah, therefore we try to really also just call it symmetric and antisymmetric and not bonding and anti-bonding because energetically works. Okay, so at least it should be there. I mean, let me just briefly, the patterns, you should see this also in the patterns, right? And now I was just showing you a line cut, symmetric, antisymmetric, nodal plane, no nodal plane. But if you look into a single atom, these extent of the Yu-Shiba-Rusinov states, you see the oscillatory behavior, but they look, well, let's say complicated. So now if you put 2 atoms together, so here that would be the topography, and if I take a larger map, well, you see the splitting of the state. You have one state which has a nodal plane, as I was showing you in the line plot before, and one where there's maximum intensity. Okay, so you also see it in the spatial extent all over, but I mean, the overall shapes are rather complicated, I would say. That's also due to the fact that, I mean, you put your atom, you have crystal field splitting that changes your symmetries, and you also have the Fermi surface of the substrate. Okay, but at least this agrees with the model of linear and symmetric and antisymmetric combination. And of course, this should hold true for all the states. So not only for the beta state, but also for the alpha state. Here, I mean, definitely you see increased intensity between the atoms. I mean, the nodal plane is very hard to see. But I mean, in the line plot, I think it was much more clear, but you see that there's also this. Okay, good. I mean, a minor, or no, it's not a minor detail, but we always look at the shapes, and this is kind of, you know, we stared at them to find always the similarities. And I said that there's always the electron in the whole part, but the patterns of the electron in the whole part, they look different. So we can also follow whether a state is on one side, a positive energy or negative energy from the shape. And here we see that we have actually change in the side where they are. And this is the hallmark of a quantum phase transition. You shift to the other side. And I would like to say that this is another clear signature that you have a quantum spin and magnetic interaction. Because otherwise, I mean, you lower the energy because you want to have Aka-Freie type of coupling. By that, you change your energy, and therefore you can go through the quantum phase. Okay, if you want to hear details, I'll be happy to talk about it. So we know that we can have hybridization of states. So that was the two dimers, but then we thought, okay, let's also look at other structures, for example, at these triangles. And there it's important to consider symmetries. Well, before I was showing you, okay, let's place an atom here, and eventually you can also place, then this is the nearest site that we can to have the same alignment with the charge density wave. But you know, if you want to go into this direction, first of all, the distance is longer, but also your symmetries change. I mean, locally, for instance, you could say, if you put this dimer up, then, okay, you have a mirror plane that goes along the dimer axis, while here you have the mirror plane between the two atoms. And the question is, does this make a difference? Well, it does, because I mean, this is the one I was showing you before. We have nicely seen the hybridization in seeing more states, and I was also showing you the nodal planes. Okay, but if we go along this direction, you lose your symmetry, right? What does it mean to hybridization of the states? Well, if we look carefully, we still, I mean, from the monomer compared to these dimers, we see an increased number of the states. That's fine. So that would be like, oh, there's hybridization. But then even the spectra on the individual atoms, they look different. That's not what we had before. But you can map it out. The atoms don't look exactly symmetric anymore. But okay, this is clear because, you know, I mean, if you look even at the topography, you see, I mean, these triangles are kind of pointing upwards. You don't expect, there's no mirror plane. The atoms should not look the same anymore. Sure.
So you were telling the previous slide that you have to put them on equivalent sides.
Yes.
And what happens if you don't put on equivalent sides?
Then it gets even more complicated. So then, I mean, so you can in principle put like just next to each other. So these Yu-Shiba-Rusinov states would already be different in energy, but we still see hybridization, but the symmetries are already very different. So the patterns look complicated, but they do hybridize, just that the images look very. Okay, so there's something, I mean, basically you can also think about this in your picture. Okay, your wave function expands and depending on how they overlap, and you think in constructive, destructive interference. And by that, in a simple model, you can also understand what happens to these pictures and the orbitals. But the interesting thing or just showcases that you can do symmetry, playing with symmetries is here. If you do triangles with this, so for instance, in this case, now, if you also map out the Yu-Shiba-Rusinov states, you see, I mean, they lost the symmetry. They are not each of them like a triangle anymore, but due to this interference with the neighboring Yu-Shiba-Rusinov state, it looks like, for instance, you lose intensity in this corner of the triangle. But interestingly, I mean, if you look at it, I mean, this looks like it's rotating in one direction. If you construct the triangle in the opposite way, then it looks like everything is rotating in the other direction. So it's kind of a chiral wave function that you can engineer just by putting the symmetries in a way that these interference terms are in the very correct way. Okay, you can build larger structures and go on with that, and just design the symmetries. But let's also look into this larger atomic chains. So first of all, I mean, maybe it's now not surprising that we can, by atom manipulation, put one atom at a time and always record all the spectra along this line. So basically cutting through the atomic chain. So these two I was showing before, single atom, two atoms, we saw that here we saw an increased number of the states. If you put a third atom, you see even more states. And eventually it will be very, very difficult to distinguish between them. But what you see, what is clearly is, no matter, so the one with the red point is the one that we add. So we add one atom, but then all the spectra along the chain change, not only locally. So this is a sign of that something really happens along the whole chain. You also, if you look into this, there's always the mirror symmetry that's preserved. And basically, you get a delocalization of these states along the whole chain. We can just pick out one and try to map it. You see that it's nicely distributed over the whole chain. So this is a sign of band formation, right? So now you do something, you put one atom more, you get delocalized states. And in the beginning, you clearly see that there was a hybridization effect. Now, when you go to longer chains, you also then do not do much anymore if you put another atom. So you kind of converge to the intensities that you eventually see. But that's also kind of intuitive, right? I mean, let's say we start with two atoms, then really every neighbor that you add matters. If you think of, nearest neighbor coupling and the next nearest neighbor coupling, but eventually, I mean, the next, I mean, this is kind of negligible. So eventually you kind of have a bulk in the chain, and therefore it shouldn't matter anymore whether you add another atom. I mean, that's kind of the feature of band formation. In different ways, you can also say, like, okay, bands. So usually, I mean, we measure the spectral function. So what is kind of local density of states. But if you think in the band structure, so now I plot here the energy as a function here of K. Then, of course, in a simple model, you should have this almost parabolic-like dispersion. These are the bands that you should get, and they have, of course, a certain bandwidth. Now, what you see most pronounced in a tunneling experiment is then, I mean, we are not K-resolved, we just, see the whole local density of states. You should see these van Hoof singularities the strongest. And well, this is kind of what we see as the limit of these bands. Okay, so now you could say, well, now you have bands. And I was saying at the beginning, if your bands, they have these two opportunities. Either you have them on one side each, and they don't overlap with the Fermi level, then it's definitely a trivial case. Or they do overlap with the Fermi level, and then it could potentially be a topological state. Well, we have seen that this alpha state that I was mentioning briefly, the sign of the state shifted to the other side of the Fermi level, and we can also track that and see that yes, this band is crossing the Fermi level. So essentially, we can say that we are in this scenario. So you can, of course, ask the question, is there a topological gap opening, and are there Majorana states? And I have to disappoint you, we see none. Yeah, so neither do we see a small gap opening, nor do we see localized end states. And well, so far I was showing you a chain that had 11 atoms. You could argue, oh, well, maybe then the end states, they hybridize or you fill your gap. But I mean, we were then going to larger atom structures up to 51 atom chains. And no, you look at it. So here now the spectra are again in this color code. Now the energy is here, and this is the spatial coordinate in horizontal. You see that there are these bands. So this is the chain I was showing you previously. So you see here these van Hoof singularities. But then no ends. At zero energy should be the energy here delta tip, because at zero energy, everything is shifted by the energy. However, what you do see is that there's something else happening with the energies. And this is what we relate to the charge density wave. because if you look closely, so here we tried to put all the atoms on maxima of the charge density wave, and that was working out here fine. But if we kind of Fourier filter this image and only look at the charge density wave maximum, you notice that yes, here we manage, the atoms are on the maximum of the charge density, while here they are on the minima. And the reason is, okay, we have this incommensurate charge density wave, so you can't put an infinite long chain always in the same registry with the charge density wave. Instead, eventually you go to the minimum, and there you have different alignments of the Shiba states of individual atoms as well as of these bands. So maybe that's interesting to see, but well, unfortunately, no signature of topological superconductor.
Sorry, just some quasi-crystal.
If we can look at it, then we should build it like that. And I think that there are. I know that there's theoretical predictions.
This incommensurability sitting on maxima and on minima. Could I look at it as being formed some kind of local order but not long range?
I think here, no, because I mean, locally it's still very periodic, and then this is one periodicity, and here's another periodicity.
It's like different commensurabilities on different regions.
But it would be interesting to look at what the crystalline spacings, like long, short, long. So, well, you know this Fibonacci. Okay. We haven't done it yet, but I think we should do it. Yeah.
On a similar note, I mean, it almost looks like you get kind of domain formation.
Yeah.
Because of this. Would that also impede Majorana searches then?
Well, that's at some point we thought it could, because you have this band bending, and then anyway you have something happening there. But maybe I should also note, so now here you have one of these chains that's rather long, and so there had been theoretical calculations how fast these Majorana states should fall off, and there they figured out it's only on a few atomic sites. So from that theoretical prediction, it shouldn't. So our kind of explanation is that why you don't see topological states is that, okay, so these are quantum spins, and previously all these Majorana, let's say, phase diagrams, they were done with classical spins. That's why I also mentioned it a little bit in the beginning. And if you have quantum spins and you add this degree of freedom, then your phase diagram, where you should see the topological phase, it really shrinks to a tiny, tiny part. So then it's not as easy anymore to just, have the bands like that, and there you are. That's our tentative explanation. Okay. I see I'm running out of time, basically. To have a bit more time. Okay, so the second part is to see what magnetic adatoms do in a very different sense. And I would, for motivating it, first like to remind you what's a diode, in the sense of that it just has a very what we call non-reciprocal behavior. So at one bias voltage you have the forward direction, and the other one you have the reverse. You essentially block the current. And well, that's all very well known in semiconductors, p junctions. Now, what would be the analog in a superconductor? And recently, there had been some kind of a push in the field, and the idea is that you maybe want to control the dissipation-less part, so the superconducting current versus the resistive part. And for that, I flash here again my phase diagram that I was showing at the very beginning. There's something like this critical current density, and so basically, if you push sufficiently current through, you can get to the normal state, or if it's smaller in this case. Now, the idea would be, what do you do, for instance, if this superconductor, or that's the ideal case. Imagine in a diode, you have really different behavior whether you push the current in this direction or in this direction. Imagine you can do something where you have a superconductor and where you have a supercurrent in one direction and a resistive part in the other one. Then your rectification ratio can be actually extremely large. So in that sense, it could be like a really ideal diode. However, I mean, at first glance, I mean, if you just have a superconductor, there's nothing that breaks the symmetries. A p-n junction, you have inversion symmetry breaking that you see. In the superconductor, you don't. But still, so there have been theoretical discussions about it that you should need to, and also practical, I will show that later, that you can break inversion symmetry, of course, by junctions, but you can also have time reversal symmetry breaking by a magnetic field, and then you can get this diode behavior. So this has been shown in layer junctions, but the question is, can you also do it at the atomic scale? So, well, of course, we have the STM, and this is what we tried to do, or found, let's better say, to be honest, because, first of all, we're interested in Josephson junctions by itself. So far, I kept the tip rather far away from my substrate, and I always talked about a quasi-particle tunneling current, so kind of, we have to go out, break electron hole pairs in order to inject electrons to hole into the substrate. So either into these Shiba states or outside of the gap. And this is a typical tunneling spectrum that you get. I should say now we measure on lead, and we use a lead tip, again at roughly 1 Kelvin. So this is what you expect when your tip is far away. Now, when you go close, what you see is a peak at 0 bias, and you see these additional side peaks at particular energies. And this is already telling you that you have a Josephson junction, because at 0 bias, you essentially can have something that is at least called a Josephson effect, a Josephson peak, because it is reminiscent of that you can transfer Cooper pairs. Okay, what are these peaks? Well, you now slightly offset your two quasi-particle density of states, and imagine you want to eject an electron from the left side to the right. Well, there's no density of states. Can't enter, but then it's reflected as a whole. It can enter as a whole here, and by that process, which is called an Andreev reflection, you also transfer 2 electrons, so you also get a current that is well inside of the gap that we see here. So that's easy to do. You just have to approach sufficiently strong with your tip to the substrate in order to establish these junctions. However, the usual case that we measure is actually not good for doing Josephson experiments in a way, because if you look into the Josephson equations, you want to measure a supercurrent. We measure, basically, what you measure a current, but as a function of voltage. Well, if you look into these equations, you see that actually if you apply a voltage, you have a phase change between your superconducting condensates. So the supercurrent itself is, here you have some critical current, but it's a sinusoidal function of the phase difference between these two condensates. But once you apply a voltage, you change this phase difference all the time. So you can't say anything about this phase dynamics of the Josephson junction, then you can't say anything about any kind of supercurrent. Because if this changes all the time, then basically you're stuck. So you don't want to change your bias voltage. So what you don't want to do, in other words, a voltage biased junction, instead you want to control the current. So we need a current biased junction. And a current biased junction, in a very simple way, you get if you just plug in a very large resistor, let's say 1 mega. Okay. Now, what do you then measure? So you control the current, and now you measure the voltage drop that you get in your STM junction. And this is a typical spectrum that we get. So we start at 0. We start to ramp our current bias. So you see that there's a slight increase, but for the moment, let's say there's almost no voltage drop. No voltage drop means supercurrent, right? There's no ohmic resistor, so there can't be any voltage drop. But suddenly you see a jump. This is what we call the switching current. And then you go to a state where you have a voltage drop. And the voltage drop now means there is a resistance. So now we go from the supercurrent to the resistive current. Okay, good. Now you're in the normal state. And this is really, so this has been in large junctions. This is the critical current. Here we have small junctions at finite temperatures. So this is why we call it the switching current. If you go down with your control current, you see that there's a huge hysteresis until you go back to the supercurrent, so the dissipationless current. And this is what we call the retrapping current. Okay, you do the same on the other side, the same happens. Okay, how do we understand this? So first of all, this shows clearly that we have current control and not voltage control. Otherwise, you should not see these jumps, and you should not see this hysteresis, because the phase would all the time vary. Okay, so how do we then explain this in terms of what's known about the Josephson effect? Well, essentially, you say that you have a tip in front of a substrate. That's fine. So you have one of your junctions should be the supercurrent, but reality is there. And the reality means that you have a finite quasi-particle current. So this is like why we put here an ohmic resistance in parallel. You also have coupling to the environment. This is why we put the capacitance here in the equivalent circuit diagram. And also you have noise and finite temperature. So this is what is here. So this is what is called the resistively and capacitively shunted Josephson junction. And if you just take your Kirchhoff's rules, current in, current out, you put up all these, supercurrent, the ohmic part, the displacement current, and the noise. That's your equation for the total current. And if you put in now the Josephson equations, then you get a function, a differential equation in the phase, because this is the voltage, it's a change of the phase. So you have here phi dot, you have here dv dt, so this is a second derivative. So basically what you get is an equation of motion of the phase, including some noise. So this is what's a Langevin equation. What does it now have to do with our experiment, you can ask? So first of all, if I measure the current, and I have here the sinusoidal behavior, so let's see if we take a potential energy curve, and this is now the phase change. And now we look into something that's the quasi-particle of the phase. Now, we have these two superconducting condensates, and if you don't apply a current bias, then your phase quasi-particle is stuck in some minimum. Okay. So, and as long as, let me remind you, according to the Josephson junctions, we only measure a voltage if we change the phase. So as long as the particle is trapped here, there's no phase change, yeah, it stays here. So if we now increase a bias current, it means that we are tilting the potential, but this phase particle can still be stuck in there. But you see already where it's going. I mean, if you tilt sufficiently strong, your quasi-particle now can run freely, and once it runs, you see it changes the phase along this axis, and therefore we see a voltage drop. Okay, so and now you see that there must be some critical tilting and some critical current, which we call the switching. Now, if you go back, you tilt back your potential, but now it's not the question on when this phase particle starts to run. It already has some energy. Just think classically of this particle in this oscillatory potential. I mean, now it's only the question of whether it was high enough here to overcome this barrier. Therefore, you get hysteresis, right? It can still be running. And you only retrap it. I mean, if there was no friction, you would only retrap once you are kind of at zero. But there's also friction, and therefore you can retrap it easier. Okay, now I told you that, no matter which direction you tilt, it's the same. But now I was also telling you that there's this finite slope that I was kind of, jumping over before. And this is the point that, well, we are in a realistic experiment. So essentially what you have is thermal activation. Eventually you can jump, and then there would be a small voltage drop. But then you can argue, but then it should be keeping running once by chance you have been able to kick it over the state. But well, as I said, there's friction, so you can retrap. And depending on your balance, so you only have a very small voltage drop, and therefore you can do this. And this has been known as frequency-dependent damping, that you can back to it. And so to be precise, according to Kautz and Martinez, we should add another branch here, which is this RC damping, to explain this. Okay, good. I mean, let me jump over this slide and come back to that later. So this was anyway on a lead junction. Now we put chromium and manganese atoms. So let's look at the chromium atom first. And you see, I mean, at first glance, well, yeah, you see hysteresis, you see a switching, you see a retrapping, fine. But if you look more carefully, I mean, first of all, the switching is reduced as compared to on the plain lead. But what is the most notable part is, okay, the switching remains symmetric at positive and negative current. But if you look into the retrapping, it's much smaller here on the negative part than on the positive part. So this is non-reciprocal. If we do it on manganese, you also have switching and retrapping currents, but now the asymmetry is exactly vice versa. So this is what we could also term that these asymmetry in the retrapping currents is a kind of non-reciprocal. So you could say it's a diode behavior in the retrapping currents, and it's opposite for manganese and chromium. Now the question is, where the heck does it come from? And what do these magnetic atoms do? Well, they induce Yu-Shiba-Rusinov states. Just to prove this again, or not again, I mean, I haven't shown you the manganese and chromium atoms on land before. These are the two spectra, again, now not in the Josephson setup, but the tip is far away. We take again DIDV spectroscopy, and you see that there are states, right? These Yu-Shiba-Rusinov states. And well, let me point out one fact. I told you in the sketch before, you can't have asymmetric states. Electron hole pair symmetry is broken. You see it really pronounced here in the intensity, right? And you see it also here in the other states, and you see it in this way on the manganese, and it's the opposite way on the chromium. Okay, so does this have any effect? Because the only thing we add Yu-Shiba-Rusinov states. But let me first say, okay, this is when we are far away. Let me first establish a Josephson junction, so we come close. And what happens to these Yu-Shiba-Rusinov states? Of course, they still persist. They don't go away just because we come with the tip close. So these are the two spectra. Again, we see, of course, the zero bias peak, which is this Josephson peak. We see multiple Andreev reflections, so gray in the background, the reference spectrum. But also you see additional peaks. And this is now actually an excitation of the Yu-Shiba-Rusinov states by an Andreev reflection. And this is what you see. And you see it also highly asymmetric, right? Because you probe by this also the weight again of your Yu-Shiba-Rusinov state. Okay, so this is very important now. So we have electron hole asymmetry due to the difference in the height of the Yu-Shiba-Rusinov states. We have transport, resonant Andreev transport through these states, obviously also when you do a current biased experiment. So what we believe, or what you can easily see there, is that, I mean, this is a process that takes quasi-particles. So it's kind of the dissipative part. The dissipative part is also the part responsible to retrap the phase particle. And we've seen precisely the asymmetry in the retrapping current. Yeah. So from that perspective, you could say it's intuitive that you get this asymmetry in the retrapping current. Well, to understand it more precisely, Felix von Oppen and his group, they have done simulations to that, but taking our experimental data. So essentially taking from here, you can also measure the IV curves, not the DIDV. So here you see the current asymmetry. It's plotted just in the two directions on one of these bias directions. You see that the current is very different for manganese and chromium, and it's opposite in the direction of the non-reciprocity. So basically, you take these curves and put them now as, remember this RCSJ model where we have the ohmic resistance? I mean, it's not an ohmic resistance. It's a resistance which depends on the orientation of the current, and it's not ohmic at all. But this curve, you just put in the RCSJ model, you solve your differential equation, and you simulate what you get. And it's exactly what we see in experiment, the same asymmetry, and we can nicely mimic what we see. Okay, with that, I think I jump over this and just finish. That are just other examples. Oops. So I hope that I have convinced you that superconductors are a nice platform to have subgap states that are nicely decoupled from any bulk states, and you can engineer atom structures by that, not only nice symmetries, but also to bands. Unfortunately, here, no topological superconductivity. And this breaking of particle hole symmetry is also important if you see it in the Josephson junction. And with that, thank you again for your attention.
We had a couple of questions already, but I would invite a few more. Christiana?
Yes. So I'm very interested in this non-linear behavior that you have in your curve, because we have been looking at Langevin equations, which is what you have there. But now, if your friction is non-ohmic, you are describing it by a fractional derivative friction. Instead of a velocity term, the non-ohmicity could be mapped by something which is fractional derivative, because it would imply sub-ohmic or super-ohmic behavior. So I'm wondering whether this could be a way to see that.
Yeah, I don't know why it should be fractional. I think it's clearly non-ohmic.
Yeah.
And this non-ohmic part goes in, but why does it have to be fractional?
Because in the Target model and a couple of system goes back,
yeah,
the spectral function of their box, it goes like eta is the friction, 1 over r in our case, times omega. The exponent of your box gives you the derivative in the Langevin equation. And it omega is ohmic dissipation from your reservoir, which would imply first derivative of position, which is velocity.
Yeah.
And anything which is non-ohmic would imply a different derivative in the friction term.
Yes, that I agree with that.
So it's not S derivative, whatever is the frequency of your spectral function that is described. Because usually, like for flux dynamics, they measure the flux flow regime when you're critical current. When you are at a bias current, that's critical, so you have flux flow.
Yeah.
Everything is just sliding. And because of that one is ohmic, they infer that in flux free regimes, when you have to jump over the barrier or through the barrier of quantum tunneling, they infer that it should be ohmic too. And then you get the Langevin equation. But if it's no ohmic when you put in impurities, maybe it is a platform to use this theory.
Okay, I think I have to discuss with you in detail. Because to me, it was just some non-ohmic part. You can engineer the non-ohmic part by saying where the Yu-Shiba-Rusinov states are, but I don't know, right? I mean, you can.
It's a dream.
Because, I mean, so I mean, the manganese and chromium, I mean, I would say, like, okay, we use them to, we saw this this asymmetry. And then we were like, oh, do we do some artifact with it? So we used the different species of manganese and chromium. It really scaled with the asymmetry of the states. But now, then we also went to, okay, let's do different atoms in different adsorption sites where the sheaf, I mean, ideally, we thought we can engineer the non-reciprocity. Ideally, I would think we need the largest asymmetry at the lowest energy. So that's what we were thinking of to engineer that, but okay, maybe we should talk in detail because for fractive to me it was just some non-linearity. Of course, in the velocity and in the friction and so on, but that's okay. I see. Good.
And I think the non-reciprocity, that's not.
Yeah, for instance. Yeah, because the non-linearity maps in a way. The way how fractional calculus can do fractional derivatives capture things non-locally.
Yeah.
And when you have non-linearities, you also have non-local. So we never have proven the equivalence, but there could be.
Okay, so you need to teach me.
Are there more questions? Okay.
Your diode, you see the switching current sort of like a sudden jump.
Yeah.
The repercussion current is usually the slow sort of increasing and then you have to jump.
Yes.
Do you know why
everything
is less jumpy?
Yeah, so I actually skipped over the histogram. So it's now, let me start with this switching, because there you start with a trapped particle and then you need thermal excitations in the first place to overcome it. And that's of course a statistical process, but once you've jumped, you've really jumped. While when you tilt it back, it's even more about the friction part, and therefore you can sometimes also it jumps again after you maybe sometimes you trap it, but then it can still be going when you go back. And therefore, I think it's broader, and also the statistics is more distributed because it's kind of a different statistics. Once it's this jumping out, which is thermal, let's say, and statistical in nature, and the one that comes back is you need the friction.
But always a jump is better not.
Sorry?
So it's always a jump, but this is just the average, not 4 events.
So this is not the average. No, this is really one phase. So it's really, but you measure, I mean, think about it like you try and you reach the particle during the time that we measure, the particle can jump or you reach up it and jump, and it's a matter. So we actually should also look at the speed of the ramping to see whether there are changes, and we try to do that in a limited range. So you automatically measure an average of the processes, but this is a single trace. So we have then histograms on where the states are to see this.
In view of time, I think we no, that's fine. In view of time, I think we are going to cut the discussion short here. Let's thank Katharina again for a wonderful talk.